Welcome to Unit 6. We'll start. We'll just go ahead through and talk about some of the things that we're doing. A couple different spelling of this dude. His name is L'Hopital. L'Hopital. And his rule is kind of simple, and I think you're going to like it, but it's going to be something that's really easy to get tangled up. So we're going to play a game today that hopefully makes it easy for you to remember. And just to tell you what's coming up, it's one of those things where it's going to make all the work we did before a lot easier. You're going to be like, why didn't we learn this sooner? And it was a vicious cycle of derivatives and limits and L'Hopital. So we'll talk about him in a minute. Next class, mean value theorem and the intermittent value theorem. Talking about applications of looking at how that derivative ends up working. When we talk about increasing and decreasing intervals after our quiz, that puts us into this conversation of starting to look at sketching curves and looking at increasing and decreasing and concavity and being able to understand what's going on there. Then we end up talking about concavity. This bottle problem is where the project is for this unit. So this project, that's going to be, you know how you love those projects. Little grade boosters, working on it in class. Some of that applied conversations. We're going to squeeze another quiz in. Make sure you understand concavity and then more sketching graphs. Please don't think that we're stopping with the homework. So go ahead and add 6-7 homework and then a review packet. I don't know. And then that Unit 6 test we're planning for with that week in March. So in between here, there's a lot of days because we have a early dismissal day and a teacher work day. And I was like, wait, is it the end of the quarter already? No, not even close. It's just professional development and teacher stuff that I get to do. So a few reminders. On the back of the page, we try to put pictures of what's coming up. So L'Hopital's rule. Yeah. So the Americanized spelling has an S in it, but we still call it L'Hopital. So here's a little preview of our mean value theorem, and here's some conversations about concavity and curve sketching. So we'll get to that as we go. All right, so just so we're all on the same page with where this unit's going. Hey, just a few quick conversations. So inevitably, we all have that third quarter slump. You guys have been students for 12 years, 13 if you count kindergarten. And definitely your last 6. When like people have been giving you actual letter grades for things, you know that typically coming out of winter, we're all feeling whoa. Anticipating the warmer weather. It's nice the sun is shining and we're not coming to work in the dark anymore. Maybe as seniors, you're just feeling tired. Just after getting through applying to colleges and maybe you're still figuring that out. Very anxious time waiting for a lot of the results or the answers to come in. And I understand how you're feeling completely, even though I went through it a lot of years ago. My kids all recently, so I get you. But you've run a good race, and I'm not going to talk over you. So every time you start talking, I'm going to stop. So we can't trip at the finish line. So 13 years plus pre-K, if that's what fits your vibe. You've run a good race, but it's too soon to stop. So if you're feeling, if you're having a hard time staying motivated, figure out a plan to continue working. Find some sort of change that you can start in your schedule, whether it's you come talk to me in the morning, do your homework with me in the morning, come to me in the afternoon when I'm here. After school, I'll do your homework then. You can't stop working. You've run a good race, don't trip the finish line. So calculus continues. And you're here in this class for a reason. Either you think you might have to take it next year at the college level. Every single little bit of learning that you can put in your box now to draw upon next year is going to matter. So we absolutely must. And starting with this, I'll be checking homework every single class period. No more of this walking around and assuming that you have it done, or no more copying my key. So I think Unit 5 was a struggle for us for so many reasons, whether it's we had too many inconsistencies in the schedule, or the weather played a part in it, and the cell day, and like COVID. I mean, there are a lot of reasons why Unit 5 was hard, but a lot of you bailed out on doing the work. And that can't be. So we're going to start this unit with a common understanding that we're going to do the work. It's calculus. You signed up for it, and you're going to see it through. And that includes doing the work, that includes paying attention in class, that includes asking questions when you don't understand, and that includes engaging and leaning in. So whatever else you're busy with during class, be a stronger person than whatever is distracting you. If it's the outside, if it's your phone, if it's a friend, if it's changing your seat, changing your view of the room. Because we'll continue going, but I'm not going to stop with the curriculum that I'm in charge of teaching and the assignments that I'm in charge of doing. Because even though you may feel like I'm done, not everybody in the class feels that way, and everybody has the right to be able to finish out what we started. So when we hit fourth quarter, we'll chill out a little bit. We'll stop with maybe the nightly homeworks, and we'll have conversations on how we can scoot through till June 1st. And we'll have those conversations then, but not yet, not now. It's too soon to stop. Are we okay on that? And I'm interested in your feedback. I'm interested, you're not my first seniors I've taught, but you're my first full senior class. So I had seniors in my other classes. So I get what you're going through. So whatever's on your mind, I'd be willing to listen to. But at the end of the day, it's still a class. And we're just over halfway. It's too soon to kind of fade out. So dig deep, lean in, and commit to learning what we're talking about. And if I start talking about something, you're like, wait, I don't understand that, go over it. Even if it's from this year, if it's from this month, if it's from, last unit, whatever, ask. Because chances are whatever question's in your head exists in other kids' heads too. Sound okay? Okay. L'Hôpital. Okay, so we're gonna kind of throw back a little bit to when we did limits. And we talked about this indeterminate form. So what I'd like you to do is read this paragraph, and I'd like you to talk to your group and remember, what did we mean by an indeterminate form? What was an indeterminate form of a limit? On your mark, set, talk, go. Indeterminate forms, who remembers? Okay, if you gotta take the limit, so let's go ahead and travel back to our limit poster, right? Our first conversation about limits, when we put our heads back into what it means to take a limit, is we're looking at where's that function going. And we wanted to check and make sure, is the limit from the left and the right the same? If it is, then we can say that we can plug that value in, right? And we can determine where's that function going. And of course, that's what happens most often. You can plug that value in, and you have that. But what we spent our time talking about was all the weird things that happen. So the limit for the positive and the negative must match in order for it to be a limit. Okay, I remember that. Because if part of the function's here and it's a piecewise function and their function's here, then we say that no limit exists. Sorry, I remember that. Sometimes I get what we call an indeterminate form, and that indeterminate form is when I get either 0 over 0 or infinity over infinity, and that was when we were like, ugh. Because I can't plug it in because I either get a 0 in the denominator or I get infinity over infinity, and I don't understand what that means and what are we doing. So we had these 3 different ways that we manipulated it, and that was where you're like, oh snap, that's a lot of pre-calc and algebra 2 coming back to haunt me. Because we had to factor, cancel out common factors, we had to find a common denominator and add the fractions, we had to use the conjugate. If it was this plus, then we did this minus, and that's what got rid of my radicals. For our trig, our sine cosine, we had all these weird little rules. Sine of x over x is equal to 1, right? Cosine of x minus 1 over x is equal to 0. So we had all of these different rules. And we had to kind of look for getting rid of one of those x values and get it out of the denominator, because that's what was causing a lot of my problems with when I plugged in my values. And that was a pain. Do you remember how much work that was? Do you remember how some of the limit problems filled up the whole board? And you're like, there's got to be a better way. Well, L'Hopital thought the same thing too. Because L'Hopital was like, dude, I got an easier way for you. So what L'Hopital says is, if you get the indeterminate form whenever you go to take a limit, instead of doing all of that work that we had to do, we can use a new rule that involves the derivative to help figure it out. First of all, let's go back and talk about our old way of doing it. If the answer is 0, 0, or infinity over infinity, then that's an indeterminate form. And that means that substitution does not provide sufficient information to determine the original limit. So our options were to factor, to multiply by the conjugate, common denominator, or use trig rules. So here's 2 examples of what it is I'm talking about. If I go to evaluate the limit as x approaches 5, and I plug in 5 in my numerator, and I plug in 5 in my denominator, I wind up with 0 over 0. And that was a problem. Which one of these strategies can help me out here? So if we go ahead and we say, okay, the limit as x approaches 5 of x minus 5 over x plus 5, x minus 5. I've now factored that denominator, crossed off my common factor, so my limit as x approaches 5 of 1 over x plus 5. When I substitute my 5 in, 1 over 5 plus 5 is when I end up with 1 over 10. Is that okay? All right. So L'Hopital's rule is going to allow you to do something a little bit different. So this is what we used to have to do when we're looking at this same exact rule. L'Hopital says, let's say that you have these two functions and you get an indeterminate form. What L'Hopital is going to allow us to do is we're going to take the derivative of each one until we end up with a value that we can use to substitute in for the limit. So if f of a is equal to 0 and g of a is equal to 0, what I can do as I'm finding the limit as x approaches a, L'Hopital says, why don't you go ahead and take the derivative of each function separately, and that'll give you your limit. Who's not here today? And that's it. So what we're going to do is we're going to take the derivative of my numerator. We're going to take the derivative of the denominator, and I'm going to substitute to find the limit. So now let's go back and revisit this one because we got this indeterminate form. And you have to make sure that you substitute every time to make sure, because you can only use L'Hopital's rule if you get that indeterminate form. If you don't get the indeterminate form and you use L'Hopital's rule, you won't get the right limit. So you have to make sure that you, again, try substituting in. And that you again get 0 over 0. So instead of dealing with factoring, instead of dealing with the conjugate, instead of dealing with trig rules or a common denominator, let's go ahead and go back to our original function and we'll take the derivative. So when we take the derivative, we end up with 1 over 2x. So L'Hopital's rule tells us it's 1 over 2x. So then as I find the limit of x approaches 5, I'm going to plug in that 5. And it works every time. So if you would rather do it this way and do your factoring and your common denominator, your conjugate, your trig rules, go ahead. But if you take the derivative of each function separately, then you can plug in that value and you can end up with that limit as x approaches this value. Now we want to make sure that you understand you're talking about two separate functions. So we're not talking about the quotient rule. We're not talking about finding the derivative of a quotient because you're finding the limit as x approaches a for these rational functions, this one over this one. And here's this handsome dude. Any French people want to help me pronounce his first name? Giuliani? Giuliani? Jacques?
I know I do.
Guillaume? Guillaume de L'Hopital. Sad story. He only lived for 43. Come on, friends. 43 years, right? He died at 43. That's 10 years younger than me. French mathematician, married a mathematician. Woke up every day, studied math. lived a dream, and the perfect life. Okay, let's do some. Let's do some. Notice we're back to taking the limits. And this is the interesting thing. You're like, why are we doing this now? So in our studies of the derivative, and as we go through talking about our graphs, looking, because limits are really about end behavior as x approaches a certain value. L'Hopital, now that we know how to take derivatives, we can go back and figure out an easier way to figure out these indeterminate limits with this shortcut. We couldn't have done it months ago because we didn't know how to take the derivative. All right, step one is what? Substitute. So as x approaches 2, 2 minus 2 over 3 times 2 cubed minus 6 times 2 squared plus 2 minus 2. So now the top one is 0. So here's 24, here's 24, minus 2, here's 0. So what we're going to do is we're going to then take the derivative and use L'Hopital's rule. What is the derivative of this numerator? 1. And the derivative of my denominator? Now you know why we did all that practice in Stinger. What was that, Billy? I can hear you mumbling. So if I have the limit as x approaches 2 of 1 over 9 times 2 squared minus 12 times 2 plus 1, then I wind up with this is 36 minus 24 plus 1. That sounds like 1 over 13, right? So now that limit, now if you want to test me and you want to go back and factor, and then go ahead and solve, you can, but you'll find out that it's a much easier way to do. And remind yourself that you're finding the derivative of the top and the bottom separately. Do not get confused with it being part of the quotient rule. All right. For example 4, as I go to find the limit of x approaches 0, if I have the sign of 6 times 0 over 0, the sign of 0, if I look at my unit circle, here's 0. My sign is equal to 0, which gives me 0 over 0, which is an indeterminate form. Now, if you remember your trig rules, you can pull out that sign of x over x, right? And then you can know that what that is equal to. But if you forget your trig rules, then let's go ahead and take the derivative of the top and bottom separately. So I wind up with 6 times what? So the derivative of sine is cosine. Derivative of sine is 6x, is the cosine is 6x. And then this chain rule times 6, I moved that 6 out front to a coefficient. So sorry if that confused you. But this 6 is the derivative of what's inside. Derivative of x is equal to 1. What is the cosine of 0? As I go to take the limit, as x approaches 0, of 6 times the cosine of 6 times 0. over 1. The cosine of 0 is 1. So it's 6 times 1, right? This is 0. 6 over 1, there's your answer of 6. All right. Check out this one. We'll talk about this one together because we wind up with the limit as x approaches 9. 9 minus 9 over square root of 9 minus 3. What do we get? 0 over 0. Our indeterminate form. So go ahead and take the derivative. Talk to your friends, see what you get. So do we agree?
Yes.
So if you struggle with this kind of stuff, don't be afraid to write it out. Because you want to make sure that you have, that's 1 divided by 1/2 is the same as 1 times 2. That's how the 2 goes up to the numerator. And anytime I have a negative exponent, if this is x to the 1/2, it becomes x to the negative 1/2. And if there's a negative exponent in my denominator, that's what moves it up to my numerator. Are we okay there? Yeah? All right. So when we talk about our next example, the limit as x approaches 0, if I have e to the 0 minus 1 all over 0 cubed, what is e to the 0? 1. 1 minus 1. That's how I get that indeterminate form first. Okay, so then when I go ahead and I take my limit as, well, let me take my derivative first. So I'm going to take my derivative of my top and bottom. The derivative of e to the x is e to the x. And the derivative of x cubed is 3x squared. So then my limit as x approaches 0, e to the 0 over 3 times 0 squared. Uh-oh. What do I get? Is that an indeterminate form? So what do we do if we end up with 0 in the denominator? Does not exist. So if we end up with a 0 in the denominator, now sometimes, and there's an example of this in your game, sometimes if we continue to get an indeterminate form, then we just take the derivative again. And you can do that. You can keep taking the second derivative, the third derivative, basically until you get rid of all the x's that are holding you up. Okay? All right. So this one's an interesting one because we're going to be able to practice that taking the derivative again with this one. All right, so if we go, the limit as x approaches infinity. Now remember when we talked about these kinds of before, we ended up looking at the end behavior of the functions, and we ended up talking about if we put a really big number in here and a really big number in here, what ends up happening. But we can go back to and start talking about here. You can say, well, I kind of get infinity over infinity, and that counts as an indeterminate form. So let's go ahead and take my derivative, because I have 2x minus 2 over 3x squared minus 10x. And the interesting thing is here, when I go to take the limit as x approaches infinity of 2x minus 2 over 3x squared minus 10x, I still get infinity over infinity. Now you can argue that there's a bigger infinity down here, just the same as you could argue that there was a bigger infinity there. But what we can do is we can take the derivative again, and we can say, okay, the derivative is 2 over 6x minus 10. So when I take the limit as x approaches infinity, I end up with 2 over, basically, when I substitute infinity in for that x. Here's where I finally end up by taking the derivative again and again. I get a constant here. So I have infinity, and what happens as my denominator approaches infinity? What happens to my number? Yeah, that goes to 0. So we end up having 0. Now, we kind of did this one with this many levels on purpose, just so you can see that we can continue taking the derivative. If you go back to your notes for Unit 2 and see what we talked about here, we talked about if there are more x's in the denominator compared to the numerator, then you know that that has a horizontal asymptote of 0. Y is equal to 0. So you know that that function will approach 0 from both directions. But if you continue getting an indeterminate form, you can continue to take the derivative to have that work out for you. All right, let's do this last one, and then we can play a game. My goal was to make sure we got through today's notes. So far, so good. All right, so the limit as x approaches pi over 2. I have 1 minus the sine of pi over 2 over the cosine of pi over 2. So if I go back to my unit circle, pi over 2 is this guy up here. Cosine 0, sine of 1. So when I go to calculate that, the sine of pi over 2 is 1. 1 minus 1 is 0. The cosine of pi over 2 is 0. And that's my indeterminate form. So let's go ahead and take the derivative. Thank you, L'Hopital. So the derivative of 1 is 0. The derivative of the opposite of the sine of x is going to be the opposite of the cosine of x. Why is that negative sign there? Think about it as a coefficient of -1. Right, so then my derivative of my cosine of x is going to be the opposite of what? So those opposites cancel out. And I wind up with putting cosine of pi over 2 is equal to 0, and the sine of pi over 2 is equal to 1. Well, I guess I should write it down. The limit as x approaches pi over 2 of the cosine of pi over 2 over the sine of pi over 2. These are both negative. So the interesting thing is you can end up with 0 as a number. That's fine. So 0 is a number if you end up having something in the denominator. That's not an indeterminate form. That's okay. Having 0 as an output because my denominator approached infinity, that's okay. Having 0 in my numerator or 0 in my denominator, that's not okay. And if you end up getting an indeterminate form, you can go ahead and continue taking the derivative more than once. Sound okay? All right. So here's the game. I'm going to give you a game board. And you're going to lay all the cards on your desk, answer side up. Pick any card, you're going to turn it over and solve the problem. And then you're going to record your problem here. And then you're going to find that answer on another card. And you're going to write that letter and you're going to keep on going. Now, theoretically, it's one of those games where you can start and end at any because it's a circuit. But we made 2 cards with the answer 0. So this one has an answer of 0, and this one has an answer of 0. So if you get a limit equals 0, I want you to pick this one first. So if you're like, wait a minute, which 0 do I pick? You're going to pick that 0 first. Sound okay? Because 2 of them have the answer of 0. So as you're going through the circuit, that's the order you should do. Sound okay? Okay.